What about the infinite binary strings? Getting back to our motivating question from the last class. The finite binary strings are countable. We can represent every natural number with a finite binary string. For the infinite binary strings, one way to show that they're uncountable would be to map them to the power set. If we can show that there's a bijection between the power set of natural numbers and the infinite binary strings, that would certainly show that they're uncountable. Can you think of how to do that? Good, yeah. Right, so one way to think about a set, if we have, here's our natural numbers. The power set of natural numbers is, for every element of that set, you have the choice whether to include it or not. And you have all combinations. To get the power set, the power set includes the empty set, which is none of those. It includes the set with 0 and nothing else. It includes the set with 1 and nothing else. We can define the power set as, for every element of the set, there's a bit string that says yes or no as that element in it. And all of those put together is the power set. So that, I think, is a pretty easy way to see that the cardinality of those two is the same, and we can't count the infinite binary strings. The other argument that is similar to the one about real numbers in the book is the diagonalization. If there is a mapping between the binary strings and the natural numbers, there should be a way of writing them down. And it should include every binary string. So to prove that that doesn't exist, what the diagonalization arguments do is say, we're going to go on the diagonal, and we're going to flip each bit. Because they're infinitely long strings, we can go forever, and we're always going to generate some string that's not in the table. If that was in the table, when we got to it, we flipped one of its bits. We're flipping one bit of every string, and because it's infinite, we can keep doing that. And we're always going to generate a string that's not in the table. So we have uncountable sets. Is there anything bigger than the set of all the binary strings, or this power set of the natural numbers? Yeah, what's bigger?
Always first guess the power set of the power set.
Sure. What Cantor proved, the power set of a set is always bigger than the set, so we can keep doing power sets. But lots of things that you would think are bigger are not. So definitely the power set of the natural numbers is bigger than the power set of the natural numbers. But the real numbers, same, and that's in the book, that proof. Certainly expanding the range of the real numbers. That's just adding 2 copies of each, right? One with a 0 in front, one with a 1 in front. We can do the same bijection there. Doesn't get bigger. This is more surprising. This is actually probably one of the most surprising ones, and we won't try to prove this. The product of the reals is also not bigger. If you think about that geometrically, that's saying the line is the same as the square. Those look like pretty different size sets. This is actually the one that the most famous quote about this area, which you might have heard. Any French speakers want to translate that? Yes.
I don't know French, but I can just kind of guess from Spanish.
Even better.
I see it, but I don't believe it.
Exactly, yeah, that's how it's usually translated. This was Cantor's quote. A lot of people think this was about showing the real numbers are uncountable or showing the power set proof. This was actually about this, showing that these two are the same size. That was the thing that he found most surprising, which is pretty surprising. And we know power sets are going to be bigger. So the big question, we've got the natural numbers. We can call that the first infinite set. And we've got the power set of natural numbers, which we know is the same as the number of reals and the same as the number of binary strings. What we don't know is if there is anything between those two. Right, so these are defined as ALF numbers. Right, ALF 0 is the smallest infinite cardinal. ALF 1 is the second smallest. It is unknown if that is the power set of the natural numbers, the cardinality of the power set of the natural numbers, or if there's something between those. And what's actually more interesting is not just that it's unknown, it's proven that it cannot be decided based on at least the commonly used axioms. So it's not that it's unknown, it's actually provably unsettlable, which is a pretty strange concept. But all these things with infinities get to be pretty strange concepts. So we won't get into that anymore in this class. That's definitely an interesting thing to ponder and to take a set theory class about someday.